in section 6.4 we're revisiting something that we learned about in advanced algebra and pre-calc, which is exponential growth and decay. And ultimately we're looking at some applications that are going to be similar to what we did in those classes, except for we're going to relate it to calculus as well. So first of all, if you're looking on your page 330, here we have the differential equation dy dt equals ky, and ultimately k being some constant. We looked at this in our previous section, in section 6.2 I believe, where we solved such a differential equation and we wound up with a formula that ultimately involved e, which we can do in just a minute. But bottom line is this particular type of differential equation is always going to lead us to a particular model, and that model should look very familiar when we get done. So if we use our separation of variables and we solve this differential equation, integrate both sides, we're going to get a natural log of absolute value of y over here and kt plus c over here. And ultimately the initial condition in this situation would just be y equals y sub 0 and t is equal to 0. So time is 0, y is equal to some initial condition, whatever it may be. So knowing that, we put our time 0 in, and we put our y sub 0 in here, we get natural log of y sub 0 over here, and then over here we just get c. So that would be our c, and therefore our natural log of absolute value of y, kt plus ln of y sub 0. And then compose both sides with e, we wind up with y over here, e to the kt plus natural log of absolute value of y sub 0. And as always, we'll use our laws of exponents, simplify, and of course this part becomes just y sub 0, so we get the model y equals y sub 0 e to the kt. So ultimately, again, this should look familiar because this is our continuous change model that we used in advanced algebra and pre-calc. And ultimately, no matter what the initial condition is, if I start with a differential equation of this type, I'm going to wind up with this model. Okay? So knowing that, then we can just go straight to the model. I mean, ultimately we could develop the model again at any time that we so chose, but ultimately if we see this kind of differential equation, it's going to lead us to this model. Right? So ultimately this is our exponential change model, if you will, or law of exponential change, as your book calls it in this particular case. And the k here is what we call the rate constant. Okay? Now let's look at a couple of problems here involving this, which ultimately, if you look at say number 2 in your book, they give us k equals negative 0.5, and they give us y sub 0 equals, or y of 0 I should say, equals 200. So again, this is number 2 from your book here on page 338. So they give us the k and they give us the initial condition, if you will. This is y sub 0, if you will. Y of 0 is the same as y sub 0, so ultimately it's the initial condition. So given that, and the question in here is to find the find the solution to the differential equation, and ultimately we could do exactly like we just did a few minutes ago, using that as our k, and solving it as such. However, knowing that we know the initial condition, we know k, and we also know the result, then we could just go 200 e to the negative 0.5 t and be done. Right? So my challenge to you would be, if you don't believe it, go ahead and try it and follow the steps here, using this as your k value and using this as your initial condition. And if you do the algebra right here that we did up top, then you'll get exactly this. So like I said, if you recognize that it's a particular type of differential equation, like dy dt equals ky, then we can go right straight to the model, knowing k, knowing the initial condition. So ultimately, if you know that, then it's a fairly easy problem. Ultimately, again, if you don't know that, you could solve it as such and get the same result. Okay. All right. Now, if you go back and look on your page 331, we have an application of this differential equation, which is related to finance, and we have been using for a number of years now the formula, and it's in different forms sometimes. Your book uses the following for compound interest, and ultimately we might have recognized it in a previous class as our amount equals principal times 1 plus r over m, and then mt. M they usually used in your previous books for compounding. Either way, it's the same equation, just different variables, but regardless. When we have compound interest, we have a principal that we put into the bank, we have a rate, interest rate of some sort. We have m, which is the number of times we compound per year, and then we have time, how long we keep the money in the bank. Now, if we just compound once per year, then keep in mind that the formula would be simply a equals P times 1 plus R to the T, which is ultimately is our growth by a percent model, because when we grow by a percent, we add 1 plus the percent, and we get our base. And keep in mind that all of these are just applications of y equals a times b to the x, which is just our general exponential model. So anytime we have exponential growth, we start with this most general model. And these others in the previous one I showed you are just variations of the same model. Okay, so bottom line is we can use this formula to figure out how much we have in the account after a certain time periods, whatever the case may be, knowing the rate, knowing the compounding times per year, and knowing the principal. Now, bottom line here is this: if we were to grow our money and compound every year, every day, every minute, and so on, we'd ultimately get more money the more times we compound per year, but surprisingly not a terribly large amount more. And what it boils down to is, what if I were to do this every minute, every second, every instant? Well, what it boils down to is if it's compounded every instant, then it leads us to a differential equation. That means that ultimately the calculus model for that would be this, where R is some constant, which ultimately is the rate. Okay? And you'll notice this has the same form as what we had just a few minutes ago. It's the form ky, if you will, a being the dependent variable in both places, just like it was earlier, R being a constant, and in this case representing the rate. Now if we go ahead and solve this differential equation, we wind up, as should not be terribly surprising, with the following model: a equals a sub 0 e to the rt. All right. So ultimately, when we have continuous compounding, okay, the differential equation that represents that, because ultimately the money is growing based on how much money is there, at every instant. And if that's the case, then we get this continuous growth model. So if we have continuous compounding, then we use the continuous change model, and specifically, we wrote in previous classes, a equals p times e to the rt, principal, rate, time. And so if we have some problems that involve this model, we recognize that it's a continuous compounding, then we just go right straight to the model. I mean, ultimately we don't have to solve this differential equation every time because we know what the solution is. It's this. So like for instance, if you look at number 6 on your page 338, they give us they tell us an initial deposit here. We have continuous compounding. It says the initial deposit is 2,000, and then it says the doubling time is 15 years. All right. So ultimately, if we use our model, we have two variables here, but again, they tell us the doubling time, and they want us to find the annual rate here, which is of course R. So doubling time, ultimately, doubling 2,000 would be 4,000, of course. And just to refresh our memory from pre-calc and algebra 2, to solve this equation, we need to divide by 2,000 first and get that e part alone. And then we natural log both sides, and ultimately natural log of e to the 15r's is 15r. And then if we divide, we get natural log of 2 divided by 15. All right, and ultimately, we're not going to present the rate at the bank as natural log of 2 over 15, put it as decimal, of course. So if we do our ln 15 divided by 2, oh, I did that backwards. Right. Let's try that again. ln 2, that is, divided by 15. And we get 0.046, so ultimately it would be 4.621%, and that would be our annual rate. All right, and then the other part they want us to do here is how much money is in here after 30 years. Well, now that we know the annual rate, we can put our 2,000 in there, and then we can use our 0.046, and just for rounding sake, I would use the entire number that the calculator gives when you do that. Or you can go back to the original ln 2 over 15, and that way there'll be no rounding errors whatsoever. And if we plug in a 30, then we're going to be able to calculate how much money is in there after 30 years. So we do our calculation, and I am in fact going to do the ln 2 over 15, keep it exact. And ultimately we're multiplying that by 30. And we'll get $8,000. So with that, that would be how much money is in the account after 30 years and so on. And again, ultimately, this is a pre-calc problem because of the fact that there's really no calculus involved other than the fact that we studied how did we get this model that came from this differential equation. Okay. All right. So there's some other problems that we're going to be dealing with here that are ultimately exponential equations that are pre-calc problems. And again, keep in mind that when we start out with any exponential growth problem or decay problem for that matter, we are starting out with our general model, a times b to the x. Okay. The next problem I want to look at, though, is a half-life problem. And there's in advanced algebra we learned how to do half-life problems with a model y equals a times 1/2, a being our initial amount, 1/2 t over half-life. And that's generally the model that we'll use. However, in this particular book, they have some applications where they want us to use the continuous change model. So if you look at number 14, for instance, they give us y equals y sub 0 e to the negative 0.005 t. Oh, one too many zeros. 0.005 t. So they give us this continuous change model, and ultimately they tell us that the they want us to find the element's half-life. So ultimately we want to know the half-life would be, again, the time it takes to go from some amount to half of that amount. So bottom line here in our equation, if we put a half here and we put 1 here, and we have e to the negative 0.5005, that is t, then we only have one variable here. So to go from 1 unit of it to a half a unit of it, it takes how much time? Well, again, it's natural log of a half, negative 0.005 t. And so if we divide, we get natural log of a half divided by negative 0.005. And if we do the calculation, we get 138.629 years. Right? So again, using this model instead of the normal half-life model, because they asked us to use this one, of course, we did that. If we were to do that with this model, we'd get a very similar answer. It wouldn't be exactly the same, but it would be very similar. In the second part of that question, though, continue on in part B here, it says that your sample will not be useful to you after 95% of their radioactive nuclei are present on the day the sample arrives. And so ultimately, the question is for about how many days after the sample arrives will you be able to use the polonium. So keep in mind that we just found the half-life, so our model now, negative 0.005 t, again, is our model here. And we want to know if the it's not going to be useful to us after 95% have disintegrated. So ultimately, again, thinking of our y and our y sub 0, if we have our 1 unit of it, and again, it could be any amount of units, but we'll call it 1 for simplicity's sake, then we want to know when that gets to 0.95. And so, again, we're going to solve it the same way as we did the previous problem. So we'll get ln of 0.95, and over here, negative 0.005. And with that, we'll go ahead and divide it out. And we get 10.259 as our t this time. So ultimately, again, our work here with the half-life model is just the same model as before. It's just a continuous change model that we're going to use. Okay? And the final example I want to look at here is another differential equation that starts out as this, and we use t and t, which seems a little weird, but that's ultimately what we use for the variables because they stand for something, which I'll indicate in just a minute. But ultimately, we have a differential equation here that is a science application for objects that are cooling. And we're not going to go through the steps to what it takes to separate and solve this differential equation. We're just going to go right to the result, which is the following equation: t sub s, t sub 0 minus t sub s, e to the negative kt. And this equation right here is what we call Newton's Newton gets credit for it. Newton's law of cooling. And what it boils down to is, again, it's a pre-calc problem because of the fact that it comes from a differential equation, but we are just given the equation here, and we're just going to use the equation for the problems that we're going to do. So ultimately, the variables, and this is a formula that you'll need to memorize because it could very well be on the non-calculator part. T here stands for the temperature of the object. T stands for the temperature of the surrounding. So if I were to bring a pie out of the oven and put it in the kitchen, the temperature of the kitchen would be the surrounding temperature. The T sub 0 would be the initial temperature when the pie comes out of the oven, if you will. Again, your surrounding temperature, K is some constant, and then T is time. So again, this is going to be our temperature. So if we knew all that other stuff and we were looking for the final temperature after a certain amount of time, then we'd be solving for big T, if you will. All right, so taking a look at one of our problems here, if you look at number 19 on your page 339, we have, so suppose that a cup of soup is it cooled from 90 degrees to 60 degrees in 10 minutes in a room whose temperature was 20. And we want to use Newton's law of cooling to answer the following questions. The question is, how much longer would it take the soup to cool to 35? All right, so with that given information here, we know that the soup cooled from 90 to 60 in 10 minutes, and we know the surrounding temperature was 20. So the surrounding temperature, there's no doubt about what we do with that. And we also know that this took 10 minutes. Okay. And we know that, keeping in mind that the temperature was 60, it started out at 90. That's the key point of making sure they put the 60 and the 90 in the right locations, because again, the T sub 0 is the initial temperature. It went from 90 to 60, so ultimately if it's cooling, this one should be bigger than this one. So if we do the math on this, ultimately we can find K, and because when we answer the first question, how much longer would it take, we're looking for a T value here, but ultimately we can't find T unless we know K, so that's what we need to do first. So if we solve this, we're going to get following. So we're going to get 4/7 on this side, e to the negative 10K. We divide by 70. And then natural log 4/7 over here. And so our final answer is natural log 4/7. 4/7, that is divided by negative 10 equals K. And of course we can get a decimal for that if you look at it in that form. And so that right there would be our K value. And if I were you, I'd store that. So store that, and we'll store it in A. And so that value is stored because we know we're going to need it here in a few minutes. So going back to the question then, it says how much longer would it take the soup to cool to 35 degrees? And so we're looking for a time in this particular instance. So if we start over with our formula here, and the way we work the formula, we really have a couple options here. We can do it at the end of the 10 minutes when the temperature is 60, and we want to know how long it takes to go from 60 to 35. We could start with the original and start with 90, and can keep in mind that there was 10 extra minutes in here, but I would start where it's at the end of the 10 minutes when the temperature is 60. So this time our 60 is our initial temperature. We want to know when it gets to 35. The temperature in the room has not changed, so that's still 20. And so all the information here we have, and we know that our negative K is our negative 0.00056 T. And again, I'm not going to use this rounded answer when I do the calculation, but ultimately I'll put it in there just so we can see that there is a K value that we just found, and that also that we're looking for time here. So doing the math on this, we get 15 here, we get 40 here, e to the negative 0.056 T. And if I divide 15/40ths, again, solving of these equations doesn't really change at all, and so we can breeze through that part of it. And so final calculation then, if we do our natural log, 15 divided by 40, and then divide that by what we stored in A, and actually we need to make that negative. And we get 17.527, and again, keep in mind this is the time, and the units are minutes. So ultimately it would take 17.527 more minutes to cool from 60 to 35. Okay. So let's take a look at part B and see if we can continue here. And it says here, instead of being left to stand in the room, the cup of the 90-degree soup was put in a freezer whose temperature is negative 15. And ultimately we want to know how long will it take to cool from 90 to 35. So if we stick this thing in the freezer, change the surrounding temperature, we ultimately have our final temperature. Again, we want it to be 35, and this time -15 is our surrounding temperature. And with the T sub 0, again it's 90 when it comes out, minus -15 again, and then e to the -0.056t, we're still looking for time. So really, in terms of solving, it's no different than the problem we just did a minute ago. Just got to make sure we put the variables in the right spots. So ultimately we get 50 over here, we get 105 over here, e to the -0.056t. And if we do our natural log on both sides after dividing, we get a natural log of 50 over 105, -0.056t, and then from there it's just a calculator problem. So if we do our natural log, 50 divided by 105, and we'll divide that by -a, we get 13.258 minutes. And keep in mind that hopefully makes some common sense, because in the previous problem it took 17 minutes to get from 60 to 35, okay? Plus the 10 minutes that we had originally to go from 90 to 35, so ultimately that was 27.527 minutes, and we put it in the freezer, it takes 13.258 minutes. So, and again, just from a common sense standpoint, that should hopefully make sense, because put it in the freezer, it should get colder quicker. So, okay, that would do it. Like I said, for the most part, just keep in mind the theme here was that you know, these equations that we're working with here to solve these problems, mainly from science, applications from a science standpoint or a finance standpoint in terms of the money problems, are essentially pre-calc problems. They come from differential equations. That's what makes them calculus problems. We only need to know how to deal with the dy dt equals ky equation. The other differential equations, we don't need to know how to solve them algebraically. We just need to know how to get to the result. So again, for instance, in the Newton's law of cooling, we don't need to do the calculus it's going to take to get to this. We just need to know this model. Okay, so you got some problems to work on, so enjoy.